Hi, today is the 2nd of July 2019, and just yesterday I posted the next section of my textbook, Visual Linear Algebra, online at my blog, infinityisreallybig.com. Section 1.7, you can see the topic is high-dimensional linear algebra. What do I mean by high-dimensional linear algebra, as opposed to, say, low-dimensional linear algebra? In low-dimensional linear algebra, it's things that we can visualize in the ordinary way, anything 3 dimensions or less. Mostly we've focused on 2-dimensional linear algebra so far, but in the last section I did generalize to 1-dimensional and 3-dimensional. But here we're going higher. 4 dimensions, 10 dimensions, 100 dimensions, 1,000,000 dimensions. We can talk about linear algebra in any arbitrary dimensions. Usually we say that's n-dimensional space, where n is a positive integer. But this might bring up a couple questions in your mind. For one thing, is such linear algebra useful? And that's what I try to argue briefly in the first paragraph here, alluding to business applications. You're going to encounter real-life business applications, for example, with flight scheduling, where you might have hundreds or even thousands of unknowns that you need to solve for. Of course, you're not going to literally do the solving yourself. You're going to program a computer to do it, or have somebody else program a computer to do it for you. But that's certainly a situation where you're going to have a lot of variables. And that's an application of high-dimensional linear algebra. But a second question related to that is, how can we possibly visualize such a high-dimensional linear algebra when we can't visualize beyond 3 dimensions? And the answer is that you can visualize by analogy, and that's going to be a theme of what we see in this section and in this video. And the way it's going to come out, initially at least, is in the context of something called a least squares problem, which is an advanced statistics topic. It's data fitting. We've got a bunch of data points. We've got 5 points here, coordinates 1, 4, 2, 3, 3, 3, 4, 2, and 5, 0. And if you plot these points, you'll see that they do not lie on a straight line in rectangular coordinates. However, they're almost along a line. There's sort of a linear trend to the data. And we want to find what's called the line of best fit, okay, which is what you see right here. So the red dots are the data points, and the blue line is the line of best fit. It's called a least squares problem because we're going to try to minimize, make least, a sum of squares. In fact, it's the sum of squares of these vertical distances that you see here. These dashed brown lines represent the errors in using the blue line to approximate the y-coordinates of these points. So take those errors, square them, and add those squares up, and minimize that sum of squares, and you will find that line. Okay, now that sounds like a calculus problem, and indeed you can solve for m and b with calculus. However, you can also solve for m and b with linear algebra, at least if you conceptualize it in the right way. And that's what I want to try to get across in both this video and this blog post. I tell you what the answer is. Y equals f of x equals negative 0.9x plus 5.1, so the slope is negative 0.9 and the y-intercept is 5.1 for this blue line. I'm not going to tell you how I find that. That's going to be a topic for a later section. But what I need to do in this section is bring it into the context of, how is it related to linear algebra? How can you think about it with linear algebra in such a way to solve for m and b? That's the point. And how is it related to higher dimensions? I mean, this seems like something we can visualize, and certainly that's true. So how is it related to higher dimensions that we can't visualize? What we want to do to move us along the direction of seeing that is to pretend, okay, something that's actually not true here. Pretend at the outset that the line does go exactly through the 5 points. Now, of course, it doesn't, but pretend, okay? If that's true, that would mean when you plug in the different x-coordinates of these 5 points into this formula right here in place of x, you get the different y-coordinates of the red dots, again, which are 4, 3, 3, 2, and 0. The x-coordinates are 1, 2, 3, 4, and 5. And these 5 linear equations would all be satisfied. This system would have a unique solution if that pretending really were right. But now it's not right, okay? This system actually has no solution. It's said to be overdetermined. There's too many equations for the number of unknowns. That's what typically happens when you've got more equations than unknowns. But can we solve it anyway? Can we find a solution that's sort of closest to being a solution to a system that doesn't have a solution? I know that sounds weird, but that's really the way to think about it. Here's a way to think about what I'm saying intuitively. Graph all 5 of these lines in a plane, not an xy plane, but an MB plane, like this. So you see the 5 lines there. There's no point of common intersection because there's no solution of the system. There's no point that satisfies all 5 equations. There are points, the red dots that you see there, that satisfy pairs of equations, intersections of 2 lines. And in fact, the red dot right over here at m equals -1 and b is 5 satisfies 3 equations. You see 3 lines going through that red dot. However, maybe we can sort of average those red dots coordinates and get another red dot, this black dot here, that is sort of the best answer, almost solving the system of equations as close as possible. That's the intuition about what we're trying to do here. Okay? How is it related to higher dimensions, though? We need to come back to linear transformations, and we are going to also do row operations. And we're also going to, in this video and in this blog post, talk about something called reduced row echelon form. That's another thing we're after with this content. The left-hand sides of these equations, this system here, can define a linear transformation. But it's a linear transformation unlike any we've seen so far. Its domain is going to be R2, 2-dimensional space, and its codomain is going to be 5-dimensional space. Something we can't visualize in a literal sense. Here's where the higher dimensions comes in. So the input is 2-dimensional. I'm going to call it x, a vector x whose components are m and b, the, say, unknown slope and the unknown intercept of the line of best fit, the linear regression line. And the output is going to be the left-hand sides of these equations up here. A 5-dimensional vector, a 5x1 matrix, okay? Now I'm writing that output next here as a linear combination. I've talked about this in recent posts. A linear combination of 2 5-dimensional vectors. And the reason that's a good thing to do is it's supposed to motivate the idea of a matrix multiplication. And that's what's down here. T of x, this linear transformation that takes a 2-dimensional input x, whose components are m and b, and gives you a 5-dimensional column vector, this one right here, as output, can be thought of as a times x, capital A times x, where capital A is this thing right there. These 2 vectors get put into a 5x2 matrix and gets multiplied by a 2x1 vector to give you a 5x1 vector. That's what we've talked about in recent posts about what matrix multiplication means. Okay, there's going to be another way we're going to conceptualize this in a little bit, so hang on for that. Let's also talk about other things that we've discussed recently. What's the image of T? The linear transformation, also called the column space of A. It does have both names. You'll see both names, and so I try to emphasize that here. And we're also going to talk about what's the kernel of T, also called the null space of A. Those will be good things to do, both to get practice in thinking about those concepts and still ultimately to relate it to the least squares problem. So what do I talk about here? I talk about, so I got a 5-dimensional vector v here that's representing the right-hand sides of the original system. 4, 3, 3, 2, 0 is the same as the right-hand sides here. 4, 3, 3, 2, 0, same as the second coordinates of these points way up here. 4, 3, 3, 2, 0. That's a 5-dimensional vector, and it turns out to not be an element of the image of the linear transformation. And you shouldn't expect it to. It would be unlikely to be in that image. Just like it's unlikely for those 5 randomly chosen lines to intersect at all at one point, have a common point of intersection. You know, the domain of T is 2 dimensions. Say that up here, and their codomain is 5 dimensions, and linear transformations are very well behaved, they're very rigid. T is not going to somehow map 2-dimensional space onto all of 5-dimensional space. That would be impossible. So you should not expect it to be an element of the image. You should expect the image of T to be probably 2-dimensional, or maybe smaller. Maybe somehow the image is going to be a plane. In fact, it will be a plane, a 2-dimensional plane through the origin of 5-dimensional space. We will visualize that by analogy here in a few minutes. That's what I talk about here. This particular vector right here is in the image, and that's because I've actually found it by plugging in a particular vector, -0.9 for m and 5.1 for b. In fact, that's the slope and intercept of the actual line of best fit. This vector, 4.2, 3.3, 2.4, 1.5, and 0.6, does happen to be in the image because it's an output of t. And in fact, here's a key point, is the unique element of the two-dimensional subspace of R5, the image which is a plane in 2 dimensions, that is closest to the vector v in a 5-dimensional space. So we need to talk about measures of distance and maybe angles, because if you think about a plane and a point not on the plane, the distance between the point and the plane is going to be along a line that's perpendicular to the plane. So maybe there's going to be angles in 5-dimensional space as well, and that is the case. So we're trying to find a vector x that makes this as small as possible. What does this represent, this magnitude here? I haven't really explained this before, though I think I need to go back and redo a little bit of section 1.2 and 1.6 to talk about this. The magnitude of the difference of two vectors is the same as the distance between them if you think of them as being points. And that is going to be as small as possible at the least squares solution when x is -0.9 and m is -0.9 and b is 5.1. Again, I don't tell you how to find that. Here's how to visualize it by analogy. Pretend this picture is a picture of 5-dimensional space. Okay, you're just using your imagination. And here's v sitting in 5-dimensional space. This plane down here, pretend, is the 2-dimensional image of the linear transformation t. And sitting inside 5-dimensional space. T of x here, this blue arrow, is the image of the least square solution. X is -0.9, 5.1. In other words, m is -0.9 and b is 5.1. And you can see, just like I hinted at a minute or two ago, the shortest distance between this point and this plane is along a line that's perpendicular to the plane. Okay? We're kind of projecting v down onto the plane, and in fact, that is the official language for the relationship between v and t of x. And again, I'm not telling you how to find x, okay? Don't think that I'm trying to tell you how to find x yet here. That's a subject for a later section. I'm just trying to get across the idea that of all the vectors in this plane, this particular one, this blue one, is as close as possible to the red one in terms of the points at their tips. This is the origin here, by the way. All right, take a breath. So now we need to talk about generalities. In fact, I don't want to spend a ton of time with this because that's something you can read. I'm trying to really focus more on the motivation here. But you can read about this. This is talking about n-dimensional space, Rn, where n can be any positive integer. 10, a million, a trillion, a goul, it doesn't matter. What is an n-dimensional vector? It's just a column matrix, a column vector, an n×1 matrix. Okay, there could be a million rows in this vector here. And Rn is the set of all such things where the entries we're taking to be real numbers. We're always doing real linear algebra in this book for the most part. Maybe some complex later, we'll see. You can add them component-wise, you can multiply them by scalars component-wise. There's properties that are satisfied, okay? And I've mentioned before that these properties are pretty easy to verify, though kind of tedious. They are worth memorizing as far as their names. Work with them enough and try to remember their names. It's a worthwhile thing to do. You'll get more out of it. We can still talk about dot product. X dot y is found to be a scalar that is the sum of the corresponding products of components. x1 times y1 plus x2 times y2, etc. The last thing that we add here is xn times y, and I should have put an extra plus sign in there. And here I'm writing with sigma notation. Whereas when we talked about magnitude or length of a vector before we invoked the Pythagorean theorem, essentially, here we are actually defining the magnitude of a vector to be the square root of the vector dotted with itself. So it might not be clear whether that's a good idea to do that definition, but by analogy with lower dimensions, maybe it is a good idea. And dot products and magnitudes do satisfy more properties, including the hardest one to verify here is something called the triangle inequality. What I've got here in this section talks about the angle between the two vectors, which kind of justifies the picture that I showed you a few minutes ago, the right angle that I drew. You might hope that in higher dimensions that these equations are still true. And they are, but they're not true because of a proof. Instead, they're true because of a definition, okay? We really define this expression to be the angle between two n-dimensional vectors instead of proving that it is, okay? Because we can't visualize it. We can't visualize a higher dimensional angle, so how do you know that this would be the angle? Well, you're going to define the angle to be that. However, there is an issue to clear up if you do that. You need to know that the input of this function, the arc cosine function, which is also called the inverse cosine function, is between -1 and 1. Okay, that is the domain of that function. So you need to know v dot w divided by the length of v times the length of w is between -1 and 1. And that is true. And it's an important enough fact that it's got a name. It's called the Cauchy-Schwarz inequality, essentially saying this inequality is true, which is equivalent to this inequality. And it's a pretty important inequality, especially in higher level math. We probably won't use it much, but it's worth mentioning here. I did do a video about it, about the idea of the proof of the Cauchy-Schwarz inequality that you can watch. And if your teacher assigns you to prove the Cauchy-Schwarz inequality, you can use this video as kind of an outline, and you need to fill in the details of that. All right. Need to talk about general linear transformations. Okay, hang with me here. There's some good stuff to come. If T is a general linear transformation from n-dimensional space as a domain to m-dimensional space as a codomain, where n and m are positive integers, then as we've discussed, there's going to be a matrix associated with that we can find the outputs of T by doing a matrix multiplication of A times a vector. That matrix is going to be an m by n matrix, it turns out, with m rows and n columns. Notice the m and the n get switched around from the domain and range order up here, domain and codomain. We need to multiply A times an n-dimensional vector to get an m-dimensional vector in the end is the idea. So using the definition of linearity, which I guess I didn't mention here, but I probably should have to re-emphasize it, you can prove that linear transformations in this situation would have to have formulas like this. Okay. Notice that these variables x1, x2 through xn have all first powers, and also notice there's no constants being added just by themselves. You gotta have a formula like that. Notice the input is n-dimensional and the output is m-dimensional, a11, a21 through am1. The m's tell you the number of rows here. They look like they're the same dimension, but they're really different. That's just a typesetting thing. Notice that this output can be thought of as a linear combination, where you've got these weights, x1, x2 through xn, of some column vectors that are m-dimensional. It's a linear combination of n m-dimensional vectors with these corresponding weights. And by what we talked about with matrix multiplication, that's what the product capital A times x is, where capital A represents this matrix here. These little a's that represent the coefficients of the x's up here go in the matrix. Okay? Here's an alternative way to write that. We can write capital A in terms of its column vectors. Notice these are bold-faced, a1, a2 through an. We can write the linear combination this way or with sigma notation. So since we're talking about linear transformations, we need to think about the most fundamental thing with these is when are they onto and when are they one-to-one. In this part right here, I talk about, this is not rigorous, but it's intuitive. When is it likely that the linear transformation is going to be one-to-one or onto? And when is it guaranteed to be either one-to-one and onto or neither? If n is bigger than m, T maps a higher dimensional space to a lower dimensional space. Rn was the domain and Rm was the codomain. It's got a kind of collapsing nature to it. It's going down in dimension. It's most definitely not one-to-one. You're going to have points in the domain that get mapped to the same point in the codomain. In fact, there'll be points in the more than one point in the kernel of T, the null space of A, that get mapped to the zero vector. On the other hand, it will turn out to be likely to be onto, though that's not guaranteed. As a trivial example that's not onto, you could map every vector to the zero vector. On the flip side, if n is less than m, then T is mapping a lower dimensional space to a higher dimensional space, and just like I hinted at 10 minutes ago or something, it's not going to expand the image, the dimension of the image. Okay, it's going to stay the same dimension or go lower. So it's most definitely not onto. On the other hand, we'll see it's likely to be on one-to-one, but that's not guaranteed. And again, we could map every vector to the zero vector, and in that case it would not be one-to-one. Finally, if the domain and codomain have the same dimension, it turns out we will see that T is likely to be both one-to-one and onto. Okay? Though again, neither property is guaranteed. However, it does turn out that these two properties of being one-to-one and onto are equivalent in this situation. That's kind of supposed to be a surprise, because being one-to-one and onto in general for nonlinear functions is certainly not equivalent. Take another deep breath. We're on to row operations and something called reduced row echelon form, which is a fundamental thing for thinking about answering questions like this in higher dimensions. Let's see here. What we want to do ultimately, for example, to decide whether this function is onto, for example, and it's not going to be onto, is, for example, show this vector, decide whether this vector is in the image or not, and it's not going to be. To do elementary row operations on the augmented matrix. Now remember what an augmented matrix is. You take the matrix of the linear transformation, you add on a column that represents the right-hand sides of the system of equations that you got the matrix from. So that's what I've got here. Notice the first two columns are the columns of capital A. And this last column here, 4, 3, 3, 2, 0, we've seen those numbers before, that's the right-hand sides of that system of equations. I want to try to do elimination. I want to try to eliminate, for example, the corresponding, it would be, I guess the variables are m and b. I want to eliminate the m's, first of all, in all the equations but the first equation. And so I can do these 4 different row operations to get a bunch of zeros below the leading one of the first row. That's certainly one thing I can do right away. And then the second thing to do is I'd like to get a coefficient of +1 here that would represent the coefficient of b in the second equation. And so I multiply the second row by -1 and get this +1 and a +5. Let's continue. The next thing you want to do is you want to try to eliminate the b coefficients from the third, fourth, and fifth equations. Makes all these things 0. These 3 row operations will give you zeros at this spot, right? These spots right here. And it's at this point that it's enough to confirm that v is not in the image. We could stop here because the third and fourth rows of this augmented matrix really represent the equations 0 times b equals 1 or 0 equals 1, which is nonsense. That's a contradiction. It's a false statement that would contradict the assumption of there being a solution if we assume there's a solution. And that means that t is not onto. That in particular this vector is not in the image. I do want to continue with more row operations here for instructional purposes, because we want to understand how to go to something called reduced row echelon form, or RREF for short. And by the way, for example, TI graphing calculators, there is an RREF function that will do this kind of calculation ultimately for you. Not only do we want zeros below the leading ones, but we also want zeros above the leading ones. So for example, I would like to make this one here a 0 that's below the leading one in the third row. And that's what I do here. I multiply row 3 by -1 and add it to row 4 and put the result in row 4 that puts a 0 right there. And now I also want to get zeros above the leading ones. So I now go upwards in my row operations. And that's what you see right here. For example, I want to get zeros above the leading one right there, here and here, by these 2 row operations. And then the leading one in the second row, get a 0 above that, make this 0 by doing this row operation. Now this matrix is in what's called reduced row echelon form, which I'll talk about the details of in a few minutes here. I certainly didn't have to do that to verify that the linear transformation was not onto, but let's talk about how to interpret this. What this augmented matrix means is the original system is equivalent to this system. M is 0, B is 0, and 0 is 1. The 0 equals 1 comes from the third row here. Now that doesn't make any sense, right? 0 does not equal 1. Again, it's a contradiction. This is still saying there's no solution. The system is inconsistent. And no, it's not saying that m and b are both 0. Okay? That's not a solution. The fact that we have a 0 equals 1 here implies that the original system did not have a solution. That's worthwhile practice to get it to reduce row echelon form and to see what it is. We will do a second example here in a few minutes. Here I have a definition of both row echelon form REF and reduced row echelon form REF for any matrix, augmented or not. Okay, it doesn't have to be an augmented matrix. It's in row echelon form if, first of all non-zero rows, in other words, rows with at least one non-zero entry, are above any rows with all zeros. All the rows with all zeros are at the bottom, like you see here. These two rows with all zeros are at the bottom. Secondly, each entry, leading entry in a row, which is the first non-zero element of that row, is in a column to the right of the leading entry in the row above it. Therefore, all the entries in a column below a leading entry are 0. So the leading entry in row 1 is this one here. It doesn't have anything above it, so it's fine. The leading entry in the row 2 is, in this REF form, is to the right of the leading entry in the row above it, and the leading entry in row 3 is to the right of the leading entries in rows 1 and 2. That's row echelon form. It's in reduced row echelon form if both 1 and 2 up here hold, plus the leading entries are 1. There's nothing about them being a 1s up here. And secondly, each leading one is the only non-zero entry in its column, so that you got to have zeros above the ones as well as below the ones, although with the first row there's nothing above it. Turns out that every matrix is row equivalent to a unique RREF matrix, and that's actually a pretty important thing. If you got a given matrix, augmented or not, and you do row operations to reduce row echelon form, you're going to get the same answer no matter what you do. Okay, as long as you don't make a mistake. Doesn't matter the order that you do the row operations in. Okay. Next is T 1-to-1. It's going to turn out that we can decide the answer to that question by determining the kernel or null space. Okay, and that's actually an important fact, that just looking at the kernel is enough. Certainly, first of all, if T is 1-to-1, the kernel will just be the 0 vector. There will be nothing else in the kernel, because certainly 0 gets mapped to 0. And secondly, being 1-to-1 means nothing else will get mapped to 0, because otherwise it wouldn't be 1-to-1. A harder thing to prove is this fact here, that it goes the other direction. If the kernel is trivial, just the 0 vector, then T is 1-to-1. And I proved that here. It's not a long proof, but it is a little tricky. Suppose T of x equals T of y. The goal is to show x equals y. The goal is to show T is 1-to-1. Subtract T of y from both sides, then use the linearity of the linear transformation, which means it's operation preserving. T of x minus y equals T of x minus T of y, which I'm assuming is 0 here. And the fact that T is 1-to-1 means x minus y must be the 0 vector, and therefore x equals y. So it's not a real long proof, but it is a little tricky. It's an important fact. Just looking at the kernel and seeing it's just the 0 vector is enough to show that T is 1-to-1. And then Theorem 1.75 summarizes Theorem 1.74 plus this observation up here to say it's ultimately really an if and only if statement. The implications go both ways. To decide then what the kernel is, do row operations, again to reduce row echelon form. But now we need to do it in the corresponding homogeneous system where the right-hand side numbers are all zeros now. This is not the original problem. It's a new problem. We're trying to figure out the kernel of the linear transformation. The row operations, however, are essentially the same. Oh, and there's a typo here. This 4 should be a 0. I will try to remember to change that right after the video. Got a column of zeros because the right-hand sides are all zeros. But nothing happens with the column zeros. It stays a column of zeros once I fix this typo here. This 4 here should be a 0. And ultimately, your reduced row echelon form looks pretty similar to the previous one, except there's no 1 here. This is a column of zeros still. And that's enough to say M is 0 and B is 0. This system does have a solution, but it's just the trivial solution, just the 0 vector. The kernel is just the 0 vector, and that's enough to say that T is 1-to-1. All right, we're getting close to being done here. If you've watched this far, you should get a prize, okay? I know it's tough. Take a breath, but I think it's worth it here. We're just focusing on another example now. And that'll be the last example. And it's something that I like to do. I like to think about the transpose of the original matrix. So I took the original matrix and made the first column of the original matrix the first row of this matrix, and the second column of the original matrix the second row of this matrix. That's called the transpose of the original matrix. And it defines a linear transformation where the domain and codomain from the first example are switched around. Now the domain is 5-dimensional space and the codomain is 2-dimensional space. So my input vector is 5-dimensional vector and my output is 2-dimensional. Okay, and here's another way you can write the output. And we want to decide, is this 1-to-1 and or onto or not? By the way, there's going to be one more theorem that you'll see here. At least one more. That's a pretty important theorem. First of all, again, you should not expect it to be 1-to-1. It's collapsing in nature. It won't be 1-to-1. It's sufficient to find the null space and show the kernel and show it's non-trivial to show it's not 1-to-1. So now the RREFs look like, the row operations to RREF look like this. Here's your starting augmented matrix. Notice the zeros over here. I switched around the two rows first of all. R1 and R2 get swapped. Then I multiply R1 by -1, add it to R2, and put the answer in R2. That gets a 0 here. Then I want to get a 0 above this leading one right there. And that's the next row operation. And this is it. This is actually RREF form. Okay? It does satisfy all those conditions of RREF. You got zeros below the leading ones and above the leading ones. These numbers don't have to be 0 over there. Okay? This is an RREF form. And it corresponds to this system of homogeneous equations. And based on what we talked about with free variables and basic variables before, that means you've got 3 free variables and 2 basic, which ultimately means the kernel is, well, you might say 3-dimensional. Is it really 3-dimensional? You can describe it in parametric vector form like this. Is this a 3-dimensional subspace of R5? You've got 3 free variables and 3 vectors that they're multiplying. It seems like maybe it should be 3-dimensional. And in fact it is, though it's not actually completely obvious. You would have to verify that these vectors, these 3 column vectors, is what's called linearly independent, which I haven't talked about yet. I will talk about it probably starting in chapter 2, which is probably going to be a couple sections from now. They don't all lie in the same 2-dimensional plane in R5, and that's going to mean this is a 3-dimensional subspace of R5. It's somehow like our space that we live in, sitting inside a 5-dimensional space, which means it's not all a 5-dimensional space. Okay? The null space is non-trivial and T is not 1-to-1. Is it onto? I said it's likely to be onto. And that could be confirmed by using arbitrary right-hand sides here. The little a and little b here are arbitrary. Can I solve this non-homogeneous or inhomogeneous system for arbitrary little a and little b, no matter what they are? If you can, then that means T is onto. And the answer is you can. Here are the row operations, and there's nothing, there's no contradiction here in the end. You can solve this. In fact, you can write the answer in parametric vector form like this. It's a 3-dimensional space inside 5-dimensional space as well. Not the same as the null space because you got this extra constant vector on there. In a sense, it's parallel to the kernel. Oh boy. Again, something we can't imagine. This is a 3-dimensional space that's somehow parallel to the 3-dimensional kernel sitting inside 5-dimensional space. This is getting pretty wild, I think. This is the last section here. Yep, then there's the exercises. Summarizing these examples in relation to something I had mentioned before, the rank nullity theorem. Just noticing a couple patterns here. In the data fitting example, the linear transformation was from R2 to R5 and had a 5×2 matrix. The null space was trivial and the image was 2-dimensional. Notice that 0 plus 2, the dimension of the null space plus the dimension of the image equals 2, which is the number of columns of A and also the dimension of the domain of T. That's not an accident, okay? With the second example, the same thing happens. We got a 2×5 matrix with 5 columns and the domain is 5-dimensional. The kernel is 3-dimensional and the image is 2-dimensional. 3 plus 2 does equal 5. The dimension of the kernel plus the dimension of the image does equal the number of columns of A, which is the same as the dimension of the domain of T. That's called the rank nullity theorem, and here's the official statement of it. Thanks for watching.